angular velocity continued. And so this is specifically 3D angular velocity. So we wrote down three identities about skew symmetric matrices. S is a skew symmetric matrix. The second property of a skew symmetric matrix is that if you have the vector A crossed with vector B, then that can be written as S of A times B. And the third property was if you have rotation metric times S of A times R transpose, then that is the same as S of R of A. Okay, and S is basically written as 0 minus AZ AY AZ0 AX with a minus sign, AY negative sign, and then AX and 0, where AX, AY, and AZ are the three components of the vector A. Okay, so we'll actually use this in the derivation today. Okay, we also used a 3-to-1 Euler angle representation, right? And we wrote down the formula for the position of a object when it is rotated by psi about z-axis, theta about y-axis, and phi about x-axis, and that comes out to be r equals r times rb, where r is in the world frame, rb is in the body frame. Okay, so that vector does not change. It basically is giving the position of a point of the object in its own frame. So if the position of a point is a, uh, with respect to a coordinate frame fixed to that object, that's simply not going to change. So what we'll do now is R is the rotation matrix. So what we'll do now next is we will take the derivative of this whole quantity with respect to time. So differentiating with respect to time, we have r dot equals r dot times rb plus r times rb dot. That's simply chain rule. But since rb does not change with time because it's fixed, it's in the world frame, that term is actually 0. So we have r dot equals r dot small r dot equals capital R dot times rb. Now we know this expression for the rotation matrix. So we know that R times R transpose I, right? Because R is orthogonal matrix. It's always satisfies this property. So if we differentiate this expression with respect to time, we have R dot times R transpose. That's the first part. And then because of chain rule, we need to also differentiate the second part equals 0. The derivative of identity is simply 0. So what we can do is we can write this expression. So rewrite this as, keep this first term as it is. Okay, now watch me carefully. So I'm going to do R transpose, and then I'm going to write transpose twice. Okay, and the transpose of transpose is the same matrix, right? And that's why I can do that, equal to 0. Okay, now what I'll do is, but by the way, what I'm trying to do here is I'm trying to find some way of writing this r dot, and that's why I'm doing this procedure of differentiating r transpose. Okay, so now I can write r dot r transpose plus. Okay, so I'm going to work with just this part. Okay, keep that transpose intact. So this term inside the bracket, this bracket can be written as R transpose times R dot times transpose. So why is that true? Well, just a second. Let me figure out something. Well, I did a mistake here. Sorry. So this should be written as R dot times R transpose. Okay. So this is a bit confusing the way it is here. So this is the same transpose. Okay, that doesn't change. What I've changed is the thing inside the blue highlight. This is what has changed. This is true because of identity, which you've proved in the first homework, in which you proved that AB transpose is same as B transpose A transpose. Okay, so if this is A and this is B, and if I take the transpose of the whole thing, then I basically switch the order. So R dot comes here, and I take the transpose of R dot transpose, so that's R dot, and then I need to take the transpose of A to get R transpose. Okay, so this is follows from this, where A equals R and B equals R dot transpose. Okay, so let me rewrite this whole expression again. So what I have, R dot R transpose plus R dot R transpose times transpose equals 0. Now, if you look at this expression here, which I wrote down, it looks a lot similar to what I written down some time back, which is S of A plus S transpose of A equals 0, right? Where S is this term, that's S, and this is S of A. And then that's the transpose equals 0. So what I'm suggesting here is that if you if you are able to express something as S plus S transpose equals 0, then the term here has to be a skew symmetric matrix. Okay, so just okay, so what I'm going to do is I'm going to write now S of A equals R R dot times R transpose. Okay, so we were able to show that that product is a skew symmetric matrix where A is some vector. Okay, we don't know what that vector is, but there is some vector out there which basically um, falls out when you take R dot and multiply it with R transpose. Okay, so now is the time when I'll actually go. Well, let me just rewrite this so that sometimes people like to use this form. So I'll take this and I'll pre-multiply both sides, or post-multiply both sides. Post-multiply by R. So I get S of A times R equals R dot R transpose R. But then R transpose R is simply the identity matrix. So I can write R dot equals S of A times R. So sometimes if you read things about rotations, you'll see that people writing this expression. So don't get too much confused with that. It's the same as this expression, just worked around. Okay, so that's just an aside. So having got an expression for R dot, what I'm going to do is I'm going to go back to this expression I wrote for the position, or the velocity, sorry. So I wrote down, let's call this 1. Okay, I'm going to rewrite 1, which is R dot equals capital R dot times RB. from 1, we wrote small r dot is capital R dot times RB. And now is the time to sub in the value of r dot. So from 2, we have r dot equals S of A times R times RB. Wait. Yeah, that's right. Now, what I'll do is I don't want to keep it in terms of RB. Okay, I'm going to try to get rid of that. We know that R equals R times RB. Okay, that's how we came to the derivation of R dot. So we can write RB equals R inverse times R, right? I just pre-multiplying by R inverse. But R inverse is the same as R transpose. So how does that happen? Well, R transpose is I. And so if you pre-multiply both sides by R inverse, you get R inverse R transpose equals R inverse. So that's pre-multiplying. And then we get, since R inverse times R is the identity matrix, we have R transpose is R inverse, and that's precisely what I subbed in here. R inverse becomes R transpose. So now we can write from 3 R dot equals S of A R times R transpose RB. So R transpose R, right? But R transpose R or R transpose is same as identity. This is identity matrix. So effectively we have R dot equals S of A times R. Okay, so what this does is it basically simplifies the formula from being R dot to S of A. And we have seen that if you have S of A times R, a skew symmetric matrix times the vector R, then this can effectively be written as the vector A crossed with R. So this is something we proved last time. A cross B is the same as S of A times B. Okay, the skew symmetric matrix, you take A, you make it into a skew symmetric matrix and multiply it with B. But then we also know that the position, the velocity, sorry, rate of change of position is omega cross R, right? This is universally true. So it's true in 2D and 3D. That is saying the velocity is omega cross R. So if you notice, let me call this 4, let me call this 5. So from 4 and 5, we can notice that A is nothing but omega. Okay, and so that A, which we had in the skew symmetric matrix, is actually the angular speed. So we can now rewrite the formula for R dot as follows. So we have R dot R transpose is S of omega. Or another way of writing that is, after post multiplying with R, we can write a formula for R dot, and that's R dot equals S of omega times R. Okay. So the point of doing this exercise is that I could have just skipped this and just given you the formula, but I thought it would be more useful and important to know how we get the angular speed in 3 dimensions. It's not that obvious. It's not simply taking the derivative of theta dot or derivative of theta like we did in 2 dimensions. It's much more complicated. So by doing this, we have expressed R dot, which is the rate of change of the rotation matrix, is a skew symmetric matrix which denotes the angular speed. So omega x, omega y, omega z is buried inside this S matrix times r. Okay, so it's much more complicated than just taking the derivative of the position of the angle. Okay, so this is just part of it. We are still not come to the point where we can write the angular speed of the system, right? So what is S omega? We know that it is omega x, omega y, omega z. But remember, so we know that this is, let me just write it down. So S of omega, we know it is the skew symmetric matrix is minus omega z, omega y, omega z, 0, omega x minus omega y, omega x, and then 0. Okay, so we know that, but how is omega related to psi dot, theta dot, phi dot, right? Remember we had rotations about the x, y, and z axis in terms of Euler angles. These are Euler angles. So we have still not expressed the omega in terms of these angles. In 2-dimension, omega was simply theta dot, but in 3-dimension, omega is not just phi dot, uh, phi dot k, because rotation, it's rotation about the z-axis, and then theta dot about y and phi dot about x. So it's not, so that's not true. So we need to still establish this relation, and that's where we sort of build up our math to get to that. So now what I'm trying to do is I'm going to try to find S of omega. Okay, and that will actually give us a formula for the angular speed in terms of these Euler angles, so rate of change of Euler angles. Okay, so this is slightly involved, so but bear with me. I'm going to start with the definition of S of omega. It's basically R dot type R transpose. Where did I get that from? It came from this expression here. Okay, so what's R? R is RZ. Okay. RZ psi, RY theta, and RX phi. Okay, so this is something we written down in the last class. So what I need to do now is take this expression, put it in here, differentiate, and then do the math. So let me just do that. So d dt, right? That's R. So that's R. So I'm going to skip this psi and theta and phi in my notation because it'll just make things too long and hard to parse. So I'm just going to write this as RZ, RY, RX. But whenever I need it, I just write it in terms of, I'll write RZ in bracket psi and so on. So that's dt times R transpose. Let me just keep it as R transpose. So now when I do this differentiation, I need to differentiate it one at a time using chain rule. So first derivative of RZ, RY, RX are constant. Then I keep RZ constant, take the derivative of Y, Rx, R transpose, and finally Rz, Ry, Rx dot time R transpose. Okay, so I have three expressions there, and I have to actually simplify each of them to actually arrive at a formula for S of omega. So what I'm going to do is I'm going to take each of them one at a time and do the math on them. So that's 1, this is 2, and that's 3. Okay, so let's start with 1. Okay, I'm going to try to simplify that first. So R Z dot Ry Rx. And I need to write the expression for R. If I take the transpose, I'll write that as RZ Ry Rx transpose. It basically comes from here. That's rz times ry times rx. That's what I wrote down. Okay, by the way, if any questions, let me know. This is slightly math heavy, but trust me that we need to do this because eventually I don't, we'll get into too many complicated things, and I want you to be able to go back to this and see where things came from, because that way uh, things later on are not so confusing. Three-dimensional rotations are in general the most hardest part of doing dynamics in 3D and controls and robotics in 3 dimension, but just bear with me. Okay, so RZ, RY, RX. Now I'm going to do is, if I have RZ, RY, RX transpose, then I'm going to use the same identity I used earlier, which is if I have AB transpose, that's B transpose, A transpose, but that's only two variables. If I want to do three variables, I just switch the order and then give them to transpose. What I mean by that is I need to do RX transpose, RY transpose, and RZ transpose. So that's how you simplify uh, three matrices transpose. We reverse the order and give transpose to each of them. Next, we notice is that this is basically the identity matrix, right? R times R transpose identity. Once that goes away, R times RY transpose is going to be the identity matrix. So that will go away, and I'll be left with only R dot Z times RZ transpose. Okay, so what's R dot Z times RZ transpose? It's at this point, let me write this as psi, psi. Okay, I'm going to try to sub in the value of R dot. I do not want R dot, I want it in terms of S. So we have written down an expression for, well, we wrote down this expression, right? So that's for R dot. If you want to find R dot Z, that's simply going to be S of the rotation associated with Z. So that's going to be psi dot. And since that rotation is about K, I would write omega times K times RZ. So this comes from R dot equals S of omega. So here omega is phi dot psi dot K, and that's because the first rotation is about the Z axis. Okay, is that clear? Let me know if you have any questions. So what I'm going to do is I use this expression to get this, and I'm going to sub this inside here, get S of dot K RZ transpose. Okay, and so this is simply the identity, and so we're left with something very, very simple, which is psi dot K. So this first term boils down to something as simple as the skew symmetric matrix of psi dot K. Okay, so which is very nice. So that's just one of the three terms. Let's go to the second term now. Okay, and I'll do it a little bit faster this time, but hopefully you'll get the hang of it as I already explained it for once. So let's do the second expression. Which is R Z R Y dot R X times R transpose. So that's R Z times R Y dot times R X times, I'm going to sub in the value of R. So it's R Z R Y R X transpose. Write down the first term as it is. Now switch switch the order of this and give each of them the transpose. So Rx transpose, Ry transpose, Rz transpose. Next we notice is that these two terms give me identity. So I've left with Rz, Ry dot, Ry transpose, Rz transpose. Okay, now I'm going to use the identity for Ry dot, which is that's simply S of something times R of Y. Okay, that thing inside the bracket is going to be the rotation about Y axis. So that's simply theta dot. And since theta dot is about the Y axis, I'll write J. Okay, Ry transpose, Rc transpose. Okay, so now this term here, Ry times Ry transpose is identity. So I'm left with Rz S of theta dot J Rz transpose. And now I'm going to use another identity which I wrote down, which is if you have Rs R transpose, that's simply S of R, sorry, S of, if you have S of A times R transpose, that's S of Ra R transpose, sorry, just S of R of A. That's the identity I'm going to use to write this as S of Rz theta dot J. Okay, so what I've effectively done is I've taken a complicated expression like this and written down in terms of a skew symmetric matrix. Okay, the last thing left now is to take the third expression, and I'm almost done. Third one. The third expression which I had to simplify was Rz Ry Rx dot R transpose, which is Rz Ry Rx dot R transpose is R Z Ry Rx transpose, that's RZ Ry Rx dot, and then I switch the order. Okay, now I do the same thing with Rx, which is Rx dot is S of something times Rx. That thing inside the bracket is going to be the rotation about X axis. So that's simply phi dot, and that since about X axis, I put the unit vector along X axis. And then I have Rx transpose, Ry transpose, Rz transpose, which is these three terms. So this thing here is the identity matrix. And then I have Rz, Ry, S of y dot I. And then what I'm going to do here is I'm going to use, well, I'm going to write this as Rz, Ry transpose. So there was a transpose, there were two transposes. What I did was I used the identity that A, B transpose is B transpose, A transpose, to basically combine these, take this B transpose, A transpose, which is this, and then wrote it as A times B. Obviously, the order is switched here. So Rz comes first and Ry goes second. So now I have this term and this term, and they look a lot alike. And I can now use the same expression I used earlier, which is Rs R transpose. So R is Rz Ry, R transpose is Rz Ry transpose, and S of A is this. Then I can write it as S times R of A. So S times R, which is this, times A is thing in the bracket. Okay, so I took a kind of complicated expression to return the S of something. What I'm going to do now is go back to my original expression. Let me call that, let me put a star here. I'm going to take this 1, which I wrote down here, S of omega, and that was 1, 2, and 3. I'm just going to write everything down, put in the value I got for 1, put the value I got for 2 and 3 after simplification, and compare them. Okay, so let me do that. Now I'm almost done. I'm almost close to getting the expression I was interested in. So now I can write S of omega equals 1 plus 2 plus 3. So 1 is S of dot K plus S of Rz theta dot J plus S of Rz Ry phi dot I. Now, there's a property of skew symmetric matrix is that if you have three skew symmetric matrix as a sum, then you can actually combine these to phi dot k plus rz theta dot j plus rz ry phi dot I. You can also show this is true when you expand S as a 3 by 3 matrix. So what this is saying is that omega, the angular speed is psi dot k plus rc theta dot j plus rz ry phi dot I. So this is finally the angular speed of the object in fixed frame. It's not simply psi dot k plus theta dot j plus phi dot I, but it involves the rotation matrix in a specific way. Okay, so this was what I was trying to get to, which is I know there's a lot of math, but I want you to appreciate that getting to that requires some matrix manipulation involving rotation matrices, and you just simply cannot add the angular speeds along each of those axes like you would in 2 dimension to get the angular velocity in 3 dimension. So I will stop here with this. I'm going to continue. If I get time to, I can continue, but I'll actually show you another way of deriving the same expression without writing 2 pages of formulas. It's more intuitive and easy to understand, but I want you to go see this process of doing the math before I actually show you the easier way of deriving the same formula. It's just basically 2 lines of writing.